In this video, we're going to be covering differential rate laws, as well as how to determine rate laws and how to apply the initial rates method to find said rate laws. So let's consider a reaction. A coefficient A times, let's say that we have these three reactants here that will be converted to products. We can express these in the form of a rate law, where rate equals K, which is the rate constant, times the concentration of A to the power of M times the concentration of B to the power of N, and the times concentration C to the power of 0. This is just the rate law. This is the rate law expression, which essentially represents this reaction here. Okay. So rate laws or equations are mathematical expressions that show the relationship between the rate of a chemical reaction to the rate constant K and the initial concentrations. Now you may notice these exponents. These are called reaction orders, which are just exponents of rate equations that describe mathematical dependence of the rate on the concentration of the reactants. Okay, so say for example, the rate of a concentration is directly proportional to the concentration of A to the power of 1 times the concentration of B to the power of 2 times concentration of C to the power of 0. From this, we can assume that the rate of the chemical reaction depends largely on the concentration of B, since its reaction exhibits the greatest order. Okay. So if M equals 1, the reaction order is first order. If N equals 2, the reaction is considered second order for concentration of B. And if O equals 0, the reaction is 0 order. Okay. Now, let's consider the proportionality constant or rate constant K. So there are a couple details about K that we want to keep in mind. K is specific to a given reaction, chemical reaction. It's temperature dependent. It's independent of the concentrations of the reactants, and the units depend on the chemical reaction itself. Okay. So with these details in mind, we can, with this information in mind, we can determine how to solve rate laws based on the initial rates method. So let's describe first what the initial rates method is. So the initial rates method is a method used for determining rate laws or equations, and this method involves measuring reaction rates for multiple experimental trials carried out using various initial concentrations of reactants. So this is kind of what you'd be looking at and dealing with here. Okay. So let's see here. Let's say we're given a chemical reaction, NO gaseous NO plus O3 gaseous yields NO2 gaseous plus O2 gas. So we'd want to determine the rate law and the rate constant for the reaction at 25 degrees Celsius. Okay, so before we do that, let's just go through a general step-by-step guide on how to solve rate laws based on the initial rates method. So I apologize for stopping the video so suddenly. There were technical issues. So before we delve into examples on how to solve rate laws, I just want to make an important note that a lot of people tend to have the misconception that stoichiometric coefficients are the same thing as reaction orders. They're not, right? Like as we see here in this in this reaction, I don't put what I mean to say is that concentration A is not equal this. Okay, so it's really important that we understand that stoichiometric coefficients are not the same thing as reaction orders. Okay. With this in mind, let's go through a step-by-step guide on how to determine and solve rate laws. Okay, so for the first step we want to do is determine the number of reactants, and then by determine the number of reactants and what reactants are being used in this chemical reaction, and then we want to propose a rate law based on the reactants in K. So this is just the generic rate law equation that we would use, where rate equals K times the concentration of A to the power of M times the concentration of B to the power of N. Now let's make an important note here that we're missing information about the reaction orders in K, which we want to find. So this is technically an incomplete rate law, or a rate law that's missing information. So to determine the reaction orders, or to solve for reaction orders and K, or just reaction orders, we want to refer to the experimental trials and results and apply rate ratios to solve for reaction orders. Okay? So when we say rate ratios, we're just literally putting two rates into a ratio formula where we're attempting to solve for the reaction orders. Now, there's several important notes that we need to make about rate ratios. We need to make sure that the trial with the bigger rate is on top, on the or quote unquote the numerator of the rate ratio for consistency, so that we're not getting odd numbers when we're solving for reaction orders. When we're solving for a reaction order of a reactant, we want to make sure that all other reactant concentrations are kept constant between trials. And this helps us discern which two trials you want to plug into a rate ratio. Which two trials you want to plug into a rate ratio. And this is a bit of a rare case. I'm not sure if I could find an example on this, but if you're unable to find two trials where the concentrations of other reactants aren't constant, you simply plug in values determined for other orders and solve for n or other reaction orders using algebra, as you would, right? If a value is close to a whole number, simply log the number and solve for m for a reaction order. So say, for example, 9.699 equals 10 to the power of m. We want to solve for m, so we log both sides. Log 9.699, which equals m log 10, and then isolate m, right? And then you just round the number up. And then we solve for K, the rate constant, by plugging in numbers for one trial and applying reaction orders. Okay? Let's go through an example of determining the rate law for a given reaction. So, a contour map showing stratospheric ozone concentration in the ozone hole that occurs over Antarctica during its spring months, right? We're wanting to determine the rate law for this chemical reaction here. Okay. So remember, let's go step by step. So the first step, we want to determine the number of reactants, or what reactants are in the chemical equation, right? And from that information, we want to propose a rate law where the rate is equal to K times the concentration of NO, which is the first reactant, times the concentration of O3, which is the second reactant. So here, this is what the rate law would look like, generally speaking, without information on K or the reaction orders M and N. So let's say we want to solve for M. M is associated with the reactant NO. So we want to find varying concentrations between trials. And we want to keep the concentration of O3 constant between when comparing trials. You'll see why in a second. So I think the most appropriate trial here would be it turns out that I'm solving for n first. So it turns out the most appropriate trial. So if I want to solve for O3, I want to solve for the reaction order for O3, which is n. If I want to solve for n, I need to find varying concentrations of O3 while concentrations of NO are kept constant. So I think the most appropriate trials here would be trial 2 and trial 1. Keep in mind here that I chose rate 2 to be the numerator, right, over rate 1, because 1.32 times 10 to the negative 4 molar concentration per second, this rate is larger than rate 2 is larger than rate 1, right? And I remember saying that we want to keep a consistent rate ratio, so I chose rate 2 over rate 1. Okay, so 1.32 times 10 to the negative 4 over 6.60 times 10 to the negative 5, right? It's clear that these units would cancel out, right? And these are the rate ratios. So this is how the rate ratio looks in its most generic form, not considering reaction orders. But when we plug in the values from the trials, this is what we get, right? K times 1.00 times 10 to the negative 6 times 6.0 times 10 to the negative 6, right? Over 1.0 times 10 to the negative 6 times 3 times 10 to the negative 6. So see here, you can see the reason why we want to have all other reacting concentrations kept the same or constant. It's because we want to cancel these out so that we can isolate, so that we can solve solely on the reactants, so that we can solely solve for one reaction order, which in this case is n, right? So when I plug in the values into a scientific calculator and I determine the number, which the result of this being 2, we see that a similar number is also applied here. So plug in the values into your calculator and you'll get 2 to the power of n, or more specifically 2 to the power of n, which equals 2 to the power of n. Now we want to solve for n, right, which is the reaction order or the exponent. So we have to apply logarithms. We have to apply log rules so that we can isolate for n. So we log both sides. We get log 2 equals log 2 to the power of n. Log 2 equals n log 2. Divide both sides, you'll get 1 equals n. So the reaction order for O3 is first order, or n equals 1. Okay? Now for the other reaction order, we want to solve for NO. Okay? We want to solve the reaction order for NO. So I chose rates 4 and 3. With rate 4 being the bigger, having the bigger rate, right? You apply a similar process. You cancel out the reaction order for n by using the same concentrations, right? 9.0 times 10 to the negative 6 over 9.0 times 10 to the negative 6. That cancels out those two n's right there. And what we're left with is 2 times 10 to the negative 6 over to the power of m over 1 times 10 to the power of negative 6 to the power of n. And what we're left with is 2 to the power of m. Same scenario, you want to log both sides. So you can isolate for m, and you get m equals 1. So the reaction order for m equals 1, or the reaction order for nitric oxide is 1. Okay. So feel free to take a screenshot of this math that's here. I know it's a lot to take in. I remember when I first started doing this, like, it was definitely a lot to comprehend. So just take it one step at a time and just keep doing practice problems so that you get the hang of solving differential rate laws. Okay. Now, the last thing we want to solve for is the rate constant, k. Now, to solve for the rate constant k, you can choose any of the 5 trials shown here, right? It doesn't have to be, in my case, I chose trial 5 to solve for the rate constant k, but it doesn't have to be that. You can choose any of the 4 other trials, trial 1, trial 2, trial 3, trial 4, and you'd still get the same answer, right? Because the rate constant is, well, constant. So when we solve for the rate constant, I chose rate trial number 5, and now I express the rate law. So the rate law is that the rate is equal to 5.94 times 10 to the negative 4 molar concentration per second, or moles per liter per second, which equals k times the concentration of NO to the power of m times the concentration of O3 to the power of n. Now we deduce that the rate, the reaction orders, is 1 for both of them. Right? So essentially k equals, the rate equals k times the concentration of NO times the concentration of O3. Therefore, to isolate for k, we just simply need to move those concentrations to the other side by dividing both sides. Okay? So essentially what I did here is 5.94 times 10 to the negative 6 molar concentration per second I divide both sides by the rate concentration, by the initial rate concentrations. Okay. This is essentially what I did. NO, O3, that's what we got, right? And then you just plug in the values from trial 5, which is 3 times 10 to the negative 6 molar concentration times 9 times 10 to the negative 6 molar concentration. And then what you should get is 2.2 times 10 to the power of 7 inverse molar concentration per second. Okay? Because we have to consider units as well, right? It's very important that you express units correctly as well. Make sure that you express your units at the end. Just to clarify, this is what I mean. 2.2 times 10 to the power of 7 moles per, or liters per mole per second. That's essentially the inverse molar concentration. Okay, that's the units that we want. That's the rate constant. Okay. So from this, we determine the reaction orders and we determine the rate constant.